All right, so let's continue with conditionals and loops. Remember this intro to programming in Python. We're going to be covering this sections. Now we'll, the notes here, or the slides, look at various sections. Conditionals, the if statement, loops, the while statement, an alternative for loop, the do while loop, nesting, and debugging. So do while we don't actually cover too much, we use too much. There are certain cases where we use it, but mostly we don't use the do while much. So let's continue. Context. So basic building blocks for programming. What have we done so far? Well, we have done primitive data types. We've done assignments, x equals y and x equals 1, assignments and statements, z equals x plus y, for example. We've done some math equations. We play around with text and inputs and IO. The next level for our building blocks for programming is conditionals and loops. So conditionals and loops, the control flow, very important part of programming. The sequence of, or a control loop is a sequence of statements that are actually executed in a program. Conditionals and loops enable us to choreograph, to control the flow based on what state or what condition you want. So a simple example that I might have here, just in a day-to-day example, I'm going to write this in pseudocode or just in comments. So when you wake up in the morning and you go outside, for example, there is a condition you first have to, for example, before I go outside, check the weather. Check the weather. This is a condition. Check the weather. Okay. If it is raining, put on a raincoat. If it is, if it is sunny, wear sunscreen, for example. Wear sunscreen, whatever you want to call it. So this is a conditional statement. You don't just go outside and just put in a raincoat. There is a condition related to this. And this, in the same way, we use this in programming as well. So on the left-hand side, we have statements. This is a, statements that go one after the other, just like a recipe in a cookbook. Statement 1, 2, 3, 4, follow each of these steps. But in real life, you need to control the flow of the statements, the method, for example. So here we have something called a Boolean, and a Boolean is what checks the condition. For example, when it was raining, it actually checked the condition, is this true? If this is true, or is it false? The words true and false fall under Boolean logic, and these two words are used throughout programming. In the same sense, if it is sunny, also check if this is true or false. And then based on if it's true or false, we will do certain things. If it's true, then put in a raincoat. Otherwise, check if it's sunny. If that's true, wear sunscreen. If false, then don't. Right? So, you can elaborate on very simple real-world conditions. So in coding, we call this Boolean logic. Something's true or something's false. If it's true, do something else. Statement 3. If false, do maybe another condition. And check if it's check the weather, or however you want to check that. And if that statement true, do statement 2. If it's false, then do statement 3. So we'll see some examples of this shortly. So again, conditionals fundamentally are based on two keywords in programming, which is true and false. Do I turn left or do I turn right? All right. So if you Google Maps, for example, and you want to maybe take a shortcut, based on your conditions, you would go left if it's true, false, go right. So our first conditional is called the if statement. right? And this is true for, I mean, what we're covering is true for all programming languages. So the if statement is a common branching structure. It evaluates a Boolean expression, Boolean as in true or false. If true, execute a statement. Else, if it's false, execute a different statement, right? This is what Boolean looks like. So if a Boolean expression is true, statement is true, then do this, else do another statement if for false. Here is a simple example from the coding Princeton Intro to Computer Science for Python. Simple example. We will test this now. We can create a new file called ops. This is, let me do a different one. Conditions of Python. So we have a program. If try to zoom this in a little bit. Get this away, I can zoom it in. If x is bigger than y, temperature is equal to x, x is equal to y is equal to 10. Anatomy of this is like the anatomy of a conditional statement. If, for example, I said do assignments x is equal to 100, y is equal to 50. Is this true? Firstly, I start with this if statement, and then I do my comparison with the two variables, x and y. So x is currently 100 and y is 50. So this is true because 100 is bigger than 50. I specify colon after my expression, and this jumps into a code block. You can see my assignments all happen after indents over here, because this is unique to this condition, this control flow. It does not happen outside this code. It's only unique to this condition. Once this condition is met, we can do something else, like import standard IO, and then do I use like standard kind of write condition met, something like that. So this is unique to this condition. So again, this is just to show you the anatomy of how if statement works. And on the right-hand side here, we have another diagram of showing how if Boolean expression is a true or false, do two separate things. So I wanted to do maybe a bit of simpler example just to help you understand this. So like weather.py. So we look at example to import standard IO. So temperature, this can be like 50, maybe 70. No, that's a bit hard to make it. Let's make it 30. So if the temperature is bigger than 30, this means it is warm. Then I'm going to just say, do not take jacket. Right, it's warm. I don't need a jacket. Do not take jacket. Else, if the statement is false, as in the temperature is less than that, then it might be cool. Maybe take a jacket with. So say send the right line. Do take a jacket. Something like that. This is trivial and silly, but this shows you, how this works. Run this code. We can say Python as a weather. See what the answer is. Do take a jacket. Is temperature is 30. We'll have to specify it maybe a bit better. Let's say if it's 40 degrees, very hot, and run the code again, then I would say that. So, a simple example, let's run that. Do not take a jacket is about 40 degrees, so it's super hot. Do not take a jacket. If it's maybe like 10 degrees, you can run it. Do, sorry, I change the wrong condition. Temperature 10 degrees, then run it again. Do take a jacket. It's going to be cold, so do take a jacket. So it's a simple real world example of how it works. And again, here is a template of Boolean statements and expressions. This was from the notes from Princeton course. This description introduces a formal notation known as a template that we will use to specify the format of Python constructs. We put within angle brackets a construct that we have already defined. This is quite, this is very, very formal for describing this, which is useful to know, to indicate that we can use any instance of that construct where specified. In this case, a Boolean expression represents an expression that evaluates to a Boolean, such as one involving a comparison operation, and a statement represents a statement. Each occurrence may represent a different statement. It is possible to make formal definitions of Boolean expressions or statements, but refrain from going into that detail. Okay, so a bit complex, technical way of kind of explaining this, but useful to know. All right, so here is an example. We will try out the if statement example, which takes in 2 arguments. So let's write this out. Let's call it, create this file, if statement. All right, let's type this out. Import sys. So again, it's good practice, to actually write this out with me if you haven't done it already. It's practice either way. Your learning skills, memory, dedication to what you're doing. Typing is essential to improving your coding skills. So y equals int sys.arg b. Again, you should not just be listening, you should be typing and coding with me. Send it either the right line. And we have these expressions, x is equal to, so we're doing some concatenation here. String of x plus, and then we have this expression before if this is L0. Okay, let's just copy and paste this line here. So I don't have to type it out. We're just going to change this one to y, into y, and L. All right, it's Karen typing out the code. So try to move this along. So this is our condition, x is x bigger than y. We get a true or false for this statement. If it's true, then t equals x. This is L2. X is equal to y. This is L3. Y equals t. Equals t, and this is L4. So let me just copy this again here. So we'll type it out. X equals string x before, oh, this is after, so it's after we can take this away, after if, and it's like it's similar, just needs to be y, just be y over here. This is y over there. Okay, that is our main function. Now let's write out our entry point for this Python file. Name. This is actually also a conditional statement, just to check if main actually exists. And we use these to modularize our code as well, so we can use it elsewhere. All right, so I think that's it. Let's run this code. Let's see what happens. I need 2 inputs. Don't know what they actually used. Let's have a look. Don't know where they ran this. Oh, 8 and 9. Okay, this is 8 and 9. 8 and 9. So how does this work? So over here we have 8 is bigger than 9 is false. So this would be false over here. Let me just 8 is bigger than 9 is false. So this would not happen at all. This would not happen. It would skip this part of code and just go back straight up to here. Nothing changed. As you can see, X is still 8, Y is still 9, X is 8 and Y is 9. So nothing changed. Okay. This is a case argument. It shows exactly what you're doing. And this is the trace that we spoke about before. I'm showing you how variables change. So there's only 2 levels of traces here, but nothing else actually changes. So level 0 and 0, 1. So over here, they specify the trace. So X is 8, still stays 8, Y is 9, still stays 9. And this condition is read is false, and then the rest is not executed. All right, descending order. This is ascending order example. Now let's do a descending. Let's run this again, but now let's run it with 7 and 5. 7 and 5. Okay, so X is now 7, Y is 5. Now X becomes 5 and Y becomes 7. So we're switching, based on this condition, we're just switching around the variables. So in this case, we have 5, well, 7 and 5, which is true. And if that is true, then T becomes comment here, then T becomes 7. X becomes 5, and Y becomes, I'm doing a trace here. It's a simple trace using comments above the code. Y becomes 7. So what do we get at the end? So the statement is true, the statement is true, 7 is bigger than 5, and then we're switching around X and Y. This is all this program is actually doing, switching around 7 and X and Y. And this is a trace that they are creating. Explain it, trace table. Last column is not part of the program's trace. It is only added for clarity. The 2 numbers are in ascending order. The if statement is not executed, nothing happens. Case 1, if the numbers are not in ascending order, the if is executed, the 2 numbers are swapped. Case number 2. All right, now here are some use cases for if statements. Continued, working out the absolute value, putting X and Y and sorting it like we've just done, finding the maximum of X and Y, error check, and finding error check for quadratic formulas. So these are examples you can try. If you want me to do it as well, leave a comment below. Examples of if statements to use to simulate a coin flip. Take a different action depending on the value of a variable. So this is flip.py comes from the Princeton course. So it's pretty straightforward code. I mean, if you can do this example, then this one should be quite straightforward as well. We import standard random library, and we define a function, and we check if the random value that is created, this creates a random value. If it's less than 0.5, then write heads. If this is true, if it's false, then write tails. And that's how we simulate a very random coin flip example. This example I did in the Princeton course, so you can also have a look. This is taken from the Princeton course as well. So example of a statement to sort. So again, this is exactly what we've done here to kind of sort values. What does the program do? So it gets to values and it checks is B less than A, and swaps first puts the value A into T, assigns A to B, and then assigns T to B. So this is just swapping the values around. This is exactly what we've done here to store the first value into T, a temporary variable, assign y to x, and then assign t to y. So just swapping around, and this is, same code we did here. So it reads to integers from the command line and prints out them in numerical order. So another example, if example, what does the following program print to the terminal? Well, this is just more in-depth, trying to understand how this works. The if example, we can do this one because this is not in the Princeton course. So let's try that out. Let me check this over here quickly. Yeah, so just to fast track the coding process, I typed it out for you already. So it's good for you to just pause now and type it out. Just for practice, but let's see what the program does. So important to Visual Libraries, we're creating our main function. We have two assignments, big X and big Y, and our condition is 3x less than 2y. If so, then we are creating two new assignments for X and Y. If this is not true, then we have two different assignments for X and Y. Then we write the output to terminal. All right, so let's see what this program does. It is called Python if example2. So output is 37 and 1376. So what does this following program do? So this was, if it's 5 and 7 is going to be false, and then this is going to be two different values. So let's try 5 and 7, 5 and 7. Minus 54 and 59. So what does the following program do? So this is this one is 417 4xy, 3y, xxy. Yeah, so they're actually all the same. I think they're just changing values around. So 417, yeah, the 417 gives you this output, and 5 and 7 gives you that output. So this is an example from the notes. Using error checks, it's useful to use error checks to check if there are any errors. Int ops is one of the files that you can get and download. So this just checks, for example, if b equals 0, then write standard terminal output, and if it's divisible by 0. So this is just checking if it's divisible by 0. So this is all that this program is effectively doing. So good program practice, use conditionals to check for and avoid runtime errors. So in this case, we are summing is summation. So if we input 5 and 2, we get everything fine. If we do 5 and 0, we cannot divide by 0. That's why we get the error. So yes, okay, it's for the condition is for the modulus. You can't divide by 0 and you can't do modulus by 0. That's why you're getting division by 0 error. So it's good practice to do that too. All right, this is the end of this section. Next one, we go on to the while statement, loops, a while statement. So the while loop. So the while loop is very useful. It executes certain statements repeatedly and until certain conditions are met. So things can happen infinity. I mean, it can go continuously without stopping. So it can evaluate a Boolean expression if true, execute the sequence statements and repeat. So this is the, I'm going to zoom in here. This is how Boolean expression is done. You have your while command. This is built into Python. Check your Boolean expression, true or false, and then do statement 1 and 2, whatever that is. And this is typically how an example, we'll do that quickly, of how a while loop looks. So let's do just a quick example of a while example. Tap that out. So this is like almost a template for while statements. Start with some initialization variable. Let me just do my import standard IO. Start with your while loop needs to know where to start from. So it can start from 4. So then I'll write a while loop and we write our condition, our Boolean expression. I is less than equal to 10. This is what it was in check, colon, enter, and then it's indented, and you write standard IO dot write a line. I think there's a typo there. It says line twice. This is not right. String I plus hello, what number they're on, and then this can be a whole bunch of statements, and then the last thing you always need in a while loop is your loop body or your iterator. So we're going to iterate I continuously until it gets to 10. And that's it. That is all. This is the standard template you always use for while loop. Let's run it. Python while example. What does it output? It outputs the word hello, starting from number 4 until the number 10. And that's all that it does. So very simple, but used, for example, to understand the anatomy of a while loop. And this is just a diagram showing how it works. You have your initial condition, Boolean expression, either true or false, and various statements that might apply to it. So your first loop, so this is from the Princeton intro course. So it is here. I'm just going to run it just to make sure it does work. Let's have a quick look what it does. So it first writes out first hello, second hello, third hello. And then if you think about maybe you have to do this 1,000 times, that's a lot of copy and pasting, typing out. So in practice, we don't do that. We use loops to do this to it for us. And this is where this loop comes in. So this is copy and paste example that was done above. So if you run this code, Python 10 hellos, again, this you can get from Princeton course, 10 hellos, you'll get your hellos from 1 to 10. So first, what does it do? The program writes 10 hellos, it accomplishes that by using a while loop. After a third line to be written, the line to differ only in the index, counting the line written in the index. This is I. Index refers to starting point, the counter for your loop. So we define a variable I to contain that index. After initializing I to 4, we enter into a while loop where we use the I to standard write line function, call and increment it each time through the loop. After the program writes 10th, I becomes 11 and the loop terminates. So let's go through this just by one iteration. So I is 4, so it checks here. Is I less than 10? Less than 10. This is true. If it's true, and then do whatever. Do this below. Perform. Do this. Okay. And then what happens is it increments I. I equals 4 plus 1, so now it becomes 5. So our next iteration is, so this was 4, becomes 5 less than equal to 10. Which is still true. So perform this thing and then iterate again. Now I equals 5 plus 1, so I becomes 6. And then we check the condition again. 6 is less than 10. Is true. And that repeats until we get to, it repeats. That repeats until we get to 11. 11 is not equal to 10. It's false. So it exits this while loop and nothing else happens after while loop. So it just exits the program. And that's it. That's all the code does. It says here, I is a loop control counter, which is true. Yeah. So this is what it does. Yeah, so this is just a diagram explaining exactly what I have just explained now, just by typing in this example. Here, I is 4 until this checks if I is less than 10. It's true, do this, do that. And then the loop starts again, checks I equals 10. So this just shows the trace example. But hopefully my comments are a bit easier to understand. But this diagram explains what you're doing. Okay, now we have an exercise a while example. What does the following program do? So we initially assign two variables, 4 and 3, and we're checking, is x bigger than 0? Well, currently x is 4, so it is. So we assign y equals y plus x, all right? And then we assign y equals y minus 1. So this will just continue because y is never checked in this expression. However, the last statement is, this is what will determine when the while loop breaks off or not. So x is equal to x minus 1. So x is currently 4. So 4 minus 1 will be 3. So it goes back to the condition. Is 3 bigger than 0? Yes, it is. Does this. Checks last condition. 3 minus 1 is 2. Is 2 bigger than 0? It is. So it does this. Is 2 minus 1 is 1. Still true. And then until it gets to 1 minus 1 is 0. Gets the condition and 0 is not bigger than 0. So it exits the while loop and writes this statement. So this is a useful exercise to see what happens. What does the following program do? So here they go step by step, just like I explained what happens. X is 3, x is 2, x is 1, x is 0, then exits the while loop. And it gives you other values at the same time. So example of a while loop to use print powers of 2. So this is code from the Princeton course, powers of 2, I should have here. There we go, powers of 2. So what does it do? It accepts a positive integer as a command line argument and or write to standard output a table showing the first n powers of 2. Okay, so again, you should be able to see the basics of a while loop again, how you initialize a variable, when must a while loop start, your condition, I is less than n, and then do this, and then your final iterator that will always check this condition. So what does it do? It increments I from 0 to n, doubles v each time. So this can be whatever it wants. So this code is actually a bit different. So let's type it out quickly. Hours to apply. Change a little bit different. And maybe just copy, so I don't waste too much time here. Copy that, powers up to. Okay. So this is fine, this is fine. So it's I0 and this is V equals 1. So that's a difference. I is less than n, it's fine. And then V is, okay, so the only difference in this code is actually just V. Otherwise, it's the exact same code. So I'm not going to go through it again. So pop quiz on while loops. Anything wrong with the following code? Yeah, so I would say that you should have your your iterator, I equals I plus 1, is not in your while loop. It's outside. So this it will actually run infinitely. So that's a problem with this code. If you didn't see that, that's a problem. I plus 1 should be inside the while loop. It's not indented. And V, due to 2 terms, V is also not indented. So that's a problem. So yeah, it says it's an infinite loop and it doesn't increment. We need a proper indentation as it shows that. Another while loop example. So V equals 1, checks for V is less than n divided by 2. This is the floor division and checks V times 2 times V. So flow chart for statement, this is what you'd get. You can maybe try this. So take some thought to convince yourself that this simple piece of code produces the desired result. You can do so by making these observations. V is always power of 2. V is never greater than n. V increases each time through a loop, so the loop must terminate. after loop terminates, 2 times v is greater than n. So yeah, you can maybe try this example. It's simple lines of code, see what you get. What does the following code do? So this looks very similar to the previous one we did above. I think like this one, the while example. There we go. Oh, not this one. Positive 2. No. Oh, I explained it. I didn't actually type it out. It looks this very similar example. And again, your x equal x minus 1 is what iterates and will stop the loop eventually. So x is minus 1, minus 2, minus 3 until the condition is minus 2. So until x is eventually smaller than minus 2, it will finish this loop. Otherwise, it just works at y, the various values for y each time. All right, so that is while loops. It's very useful. We can use a lot more examples of while loops to come. So the for loop. All right, so what is this? So the for loop, this is C code, showing you what a for loop looks like. And just like as a while loop, loops allow you to do something multiple times. And this is a little silly example where somebody is supposed to write, I will not throw paper airplanes in class. So instead of writing it out 1,000 times, they wrote a for loop to do that for them. So this in C. Python looks kind of similar, but we'll get to that. So the for loop. So the for loop is an alternative repetitive structure. Executes an initial statement, evaluates a Boolean expression, just like a while loop, and if true, executes a sequence of statements, then executes an increment statement and repeats. So this is what a for loop or the structure of for loop looks like. We have a for statement, then some variable, and then some range that we want to work with, starts and stops, and our statements, whatever happens in here. So our loop, this is a loop continuation condition, just like on a while loop. Here's another structure in terms of a diagram, block diagram, initialize some variable, have a Boolean expression, and then again, you have 2 conditions, is it true or false, and the various statements and the increment. So the one difference is the increment, the value at the increments is actually built inside of a for loop. It's not as explicit as shown as a while loop. And that to me of a for loop. So let us do this example here. Let's do powers of 2. Powers of 2. Let's do for loop. For loop.py. So that's going to be import code here that we need. You say import standard IO, power equals 1 for I in range of n plus 1. And then standard IO.write line, pass the string, convert it to a text. I, and then plus empty brackets, use double quotes, and then string power value, and then power is star equal to, sorry, star equal to, which is the same as saying power equals power times 2. All right, so let's see if this runs. I made a mistake here. I forgot my colon, which we need, and we need this, and we need that. Let's run our code. We type Python, for example. Name n is not defined. So maybe let's make n equal 5. And we get the powers of 2 until n is 5. So instead of 2. So this is anatomy. Start with a for loop, start with your variable that will iterate. In this case, we don't need to initialize it here. We initialize it inside the for loop statement. And we have a range that begins from start and stops. If you just mention the one value, it assumes the starting point is 0. And we write some text to the terminal. And we work out the power of 2. Again, this is one way to do it shorthand, but ultimately you're saying power equals power times 2. So it says that this is a compound assignment. What does it print? 0, 1, 2, 3, 8 as done. For loops are subdivisions of a ruler. So this we actually did in the, I think on the first lessons, we did this example. Create subdivisions of a ruler. To initialize a ruler to one space for each value I from 1 to n, send I between 2 copies of ruler. This is the code you can get over here. So this was example we did previously, this ruler problem. So let me just move this across so we can see what's going on. So this was our initial ruler problem, and we said, okay, well, let's make this more useful and do a for loop instead. So let's maybe create a new file. Here, say, for ruler example. Let's copy and paste the code here. We're not going to use this method. We're going to use a method here. We import standard IO, which is done. And we define def name, get a value from terminal, sys.argv. Some input. The ruler is these spaces. And then for I in range of I, the starting point. This is I want to start my for loop at 1, and I go until n plus 1. And ruler is ruler plus string I plus ruler, and exit my for loop code block and say standard IO that write a line and ruler, and I create an entry point on my code. Name. This is also a name condition. Okay, so let's see what happens if I run this. So this is my for loop example. For loop ruler. Okay, I'm not finding something. Import sys. I forgot my library. It's complaining about that. Import sys. Let's have a look. Clear this again. The Python for ruler example 5. Ruler is not defined. Oh, here we go. Spelling mistake. Again. And I didn't get an output. Let's see what mistake I made. So the mistake I made was I didn't spell ruler correctly, and it didn't give me an error because I'm actually assigning a new variable. That's why it worked. So that's the mistake I made. Run it again, and there we go. We get a lot of ruler. We get a lot easier to create a ruler in this way than before. That's how the code works. You can see the end of a loop trace as well and the Python code. So do not run this. This will never finish because if this continues, it's been a lot of values you'll get. So do not do anything big. So some loop examples. We have first write n plus 1 powers of 2, which is the example I did already. find the largest power of 2 less than or equal to n, write the sum value. This is a pretty common example to work out the sum of a number, write a product of a number, write a table of n plus function values. So the sum and product, these are mathematical equations when you have the epsilon or the sum symbol itself, and you have these math equations. This is what it's referring to. But the rule function, this is exactly what we did. So now we have a question that says, use a for loop to compute 1 plus 3 plus 5 until n. Assume n is odd and has already been defined. So what does the following program do? So let's see. All right, so let's try and work out this example. I'm going to copy this code just because it's generic. We're going to create a new file here called loop exercise1.py. Paste it here. Begin with this stuff. So we can just say that really, we can say total value is 0, for example. We can say for I in range, start from 1 till n plus 1, skip 2. So start at 1, step by 2 until I get to n plus 1. And then total will be total plus 1, say n is equal to 5, for example. Let's see if this code works. So Python loop example. I forgot something here. I got a for loop and also got to indent. There we go. I'm not printing out anything, so standard IO dot write line. So total. So it'll be 3. Make this a larger, and then this is how we would compute this sum. Assume n is odd. We've done that example, and has been defined. So pop quiz, what does the following program do? Well, we can see it assigns 2 variables and starts from, here's a range of I. I must start from 0 and end at 11. This is a little useful exercise I want to just show you when you work on the for loop. Let's go to our interactive environment. Let's say I have for I in range of 0 to 5. Print. I'm using print because I haven't imported library yet. So if you look at this, this is very useful too. First, understand I must start from 0, which it does, and it must increment until 5, so not equal to 5, until it's less than 5. That's why it says 0, 1, 2, 3, 4. Right? When it gets to 5, it exits the for loop. So very important to understand. So this example, it'll never reach 11. It will stop at 10. So what does this do? This code writes the values 0 and works out these expressions f plus g and g equals f minus g. So this works out these expressions from 0 until 10. And there's a trace table that they developed for the various values until 10, as I showed you, so 0 to 10, and how F changes, then how G changes. So simple to write this code out and make sure you get the same output. Right, now we do a do-while loop, and a do-while loop isn't really used that much, but it has some useful cases. So a do-while loop is a loop and a half. So do-while loop, a less common structure. So this common structure, it's a executes sequence of statements, checks the loop condition, and repeats. So in this case, a do-while loop looks like this. So while the statement is true, do the statement, and if the expression is met, then break. So break will force the while loop to actually exit. That's what it does. It forces to exit. So looks like a while loop, but using the break command, you can actually force it to break. You can also use break statement inside of here in our if for statement, but say if I equals 3, 3, I can also say break. So it won't actually reach n plus 1, it will break at 3. So this example that you can use. So break stops the loop and exits the code block. In terms of the block diagram, you have statement, second statement, your expression is either true or false, and it does a loop. So do-while loop, less common repetition structure, executes sequence of statements, checks loop condition, and repeats. So this is an example in Princeton notes to work out a random value for x and y on a circle. You also create an infinite loop. So this is the one thing to always check. If you are in an infinite loop, it says you can just do Control-C on your terminal and it should break it. But this condition, unfortunately, is never met. And that's why I should never do that, because the problem with this code is that I starts at 4. So I is 4. If you want to do a trace diagram, I is 4. It checks I is 4, so it's bigger than 3, so that's correct. So this expression is true. So it goes in the code block, prints this out, and then increments I plus 1, which is now 5. So it checks, 5 is bigger than 3, so it continues. And it continues forever. It never breaks. So this is an infinite loop. So this is incorrect how it's coded, because it will never, it will never exit the while loop. Nesting. So nesting conditionals and loops. So you can use loops and conditionals together. How does it work? And you can use list loops within loops as well. So conditionals enable you to do 2n sequence of operations with n lines. So what does that mean? So with more sophisticated programs, nest conditionals within conditionals, nest loops with loops, nest conditionals within loops within loops. So loops enable you to do an operation n times using only 2 lines of code, which is useful. So here's is an example of creating a whole bunch, looks like 10 if statements, 10 separate if statements, over and over, checking if this condition is met. And here is a simple summation for working out the sum from 1 to 1024. So how do nested loop statements work? Here's an example of a nested loop statement where you have an input and you have 2 for loops, and then you have an if statements as well. In this case, if else statements with 2 conditions, true or false. So first for loop is you write the ith line, and for j, write the jth entry of the line. So it will actually check, make I equals 1, and then do j equals j is 1 until n plus 1. So this will this part of the code will, will perform its function. Once it exits the loop, it actually goes back to this for loop and increments I. So I becomes 2, then goes back to J, and then does your loop again, and then again until this loop is completed. When this exit, it goes back to this for loop and continues until this expression is false. So flow diagram of divisor pattern. So I think hopefully should have a divisor pattern here. So we did have a divisor. So this is from the Princeton note. So this is a divisor pattern. So it accepts an integer, command argument, and then writes to standard output an n by n table with an asterisk in a row and I column. If either I divides j or j divides I. So this is a way to draw little squares and images. So let's first run it and see what we get. I haven't input anything, so make it 5. So I'm drawing a little diagram. So what first happens is first I equals 1. And then j equals 1, and it does this code. Checks this condition if it's true or false, either does a star or space, and then comes back and increments j equals 2. Importantly, I is still 1. I hasn't changed. It's going, so I is the ith line, so this can be either your rows and j is your columns. So it does this until j is equal to n plus 1. Once it exits this loop, it will increment this loop. So now I becomes 2 and it repeats the process. It starts again, j equals 1, 2, and until it gets to the end. So this process repeats, and this is a common and nested for loop structure. The flow diagram showing the process. We start with I equals n, check if it's less than n. If no, exit. If yes, then do j equals 1. And then do your j part of the function. When that exits, then increment. Then you increment I equals I plus 1 and continue the process until the program ends. So you trace over division pattern, you can see it over here. So I stays 1 for quite a while, and then j changes. These are outputs we get and stars. And then once that's completed, then I increments to 2. You get 1, 2, 3, and the values for I modulus j and j modulus I, and get your outputs and then until 3 if n was equal to 3. So modify a divisor pattern to print the following pattern. So tip to use de Moivre's law. So they said using de Moivre's law, which is not to use not A plus A or B. So not A and not B. So, all right, so let's see what we can use here with, I think just changing this. If j equals this, what we currently have, and I think this is probably de Moivre's law, where you say not equal to 0 and j not equal to I. So let's see if that makes a difference. Just run it again. Made a mistake. Should be exclamation mark. Not. Run it again. And yeah, so I guess this is de Moivre's law. Just changing that. So nested if statements to an example to pay a certain tax rate depending on income level. So we have an example here. 5 mutually exclusive alternatives. If your income is 0 to this one, 47, 114, 174, 174, 131, 019. So if you have these various incomes, then your tax rate is adjusted accordingly. So this is a very useful example. Sure we can do that one because it's a useful example just to see how nested if statements work. So this is like a tax example. Just copy that. I can just say port standard IO. So if our rate is 0.0, and income, we'll start with maybe 30,000. If you want to, we're going to try this out. If you want to specify lots of numbers, you can actually separate thousands with underscore. So let's see if that works. It hopefully does work. So, but let's do the nested statement. So let's say if income, I don't actually need brackets, income less than 4,750, then my rate is equal to 0.22. What they are doing is fine. They are writing this command in one line, but I prefer just to do it in that line over here. So it just makes it more distinct what you're changing. Then if I want another condition, else, which just stands for else if, I can just copy this here so I don't have to keep it popping out. Else if is 114, 114, 650. Then my rate is 0.28. And so on. I'm not going to write all those examples. I think you can get the idea. And then the last one is else rate is 0.35 if it's a larger amount. Okay, let's see if that works. Run tax example. Example one. I'm going to point anything out. Let's see what the rate is. Standard IO dot right line. And what rate do we have for 30,000? The rate is initially 0, so it should be, why is it 0.22? Yes, because it is less. 30,000 is less than this amount. So again, we can also add this here just to maybe split it up. I find it something useful. It's a little trick in Python to use underscore to split thousands, just easily readable. So 0.22, if I make it maybe 50,000, run that, then it's right to 0.28. If it's a large amount, 200,000, then it should be the highest rate, 0.35. So nice little example, let's just illustrate nested if statements. So this example shows another situation, but coded incorrectly, and why we use nested if statements. So let's say our rate is initial rate starts at 0.35. Why would it not be a good idea to have to not use if statements? So for income, let's say it's 0.35. Well, the one thing is there's no else statement, so that would not work. And also, if we work out the wrong graduated income tax without the else statement, because what happens here, once it finds its condition, it exits the for loop. Here, it doesn't. It will actually give us, if I say like 30,000, it will go through each one and adjust the rate. So 30,000 is still less than 300,000 and 11,950. So the last rate will be 0.33. So which would be incorrect. We want the if condition to exit once it's found the correct rate. Nested conditionals and loops. Any statement within a conditional loop or loop may itself be a conditional or loop statement. Enables complex control flows, adds to challenges of debugging. So here we have a for loop with a while statement and an if statement to work out a gambler's ruin simulation. So this is a Gamma-Zero simulation, combining an if statement, if statement and an else statement, as well as a while statement and a for statement. So what for, this allows you to limit the amount of times your loop happens, and while allows you to loop through multiple times your expression you want to do. So if else statement within a while loop and within a for loop. So math applications. We have a harmonic example. Again, this is in the Princeton notes. As I've shown you, this is a typical for math calculations. The sum of I equals 1 until n for 1 over I. To do these type of math calculations, for loop is ideal. And this is a format that we've done before, or a format that you can do. This is in the notes to do the harmonic examples. Let me just see if it is here. The harmonic, oh, there it is already. So there's a harmonic example, get the input for n, and then get for I in the range of that value, and it work out your total. Again, if you're not too familiar with the shortcut method, you can use also just say total equals total plus 1 divided by I will give you the same result, and it works out the harmonic. So the program accepts integer n as a command line argument and writes the nth harmonic number that is known from a mathematical analysis to be about logarithm n plus 0.5721 or large n. And note another output as what we get. So what is the following command Python 3 harmonic print to determine when executed? Well, let's have a look. Let's see what result we get. Harmonic 3, get 1.833 recurring. So Newton-Raphson method, another mathematical application of for loops. Goal, find the root of any function, start with estimate t0, draw a line tangent to curve at x equal ti, see ti to be x coordinate where the line intersects the x-axis, and repeat until the desired precision is found. So technical conditions, fx is smooth, t is a good estimate. So this is your math equations you need to figure out a way, and this is your proof, figure out a way to work this out. And this would be ideal methodology for working this out using for loops. This is the final substitution you can do to work that out. So while loops for square root. So Newton-Raphson method to compute square root of c to initialize t as 0, repeat up to desired precision. And there's examples taken from here, substitution to work out the square root, well, mass without the square root. There's examples of working it by hand. So I should have a square root example here, I think. Square root, there it is. So this is the implementation of this expression over here. T is 1 over 2, c over t plus t. And the condition is t minus c over 2 must be greater than epsilon times t. That is condition. Here's an example. So if we can run it as well, Python square root 2, we get 1.41 and whatnot. So useful example to work through. Just note what we are looking for. Our conditional, this is an expression we are trying to, which is find true or false. Just note there's no iterator here. Very interestingly, there's no iterator. The iterator, it will iterate by itself until the condition is met. So you can replace the t by the average of t and c over t. So absolute value ensures error tolerance of correct magnitude and using epsilon. And this is the trace output table that you can see. So exercise even while loop. Write a while loop that prints out all the even numbers between 1 and n. Assume n has already been defined. Include n in your calculation. So here's a nice example. Writing it out. to write a while loop that prints out all even numbers between 1 and n. So to check a number is even, the only trick to this is the modulus. To see if something is divisible by 2, it is even. So this is the trick. This is the formula you need to work off to get all the even numbers, or the odd numbers when written out, because they're not divisible by 2. So hopefully you can code that out yourself, because it looks quite straightforward. Convert to binary. So this is also a piece of code from I should have here from the Princeton notes. So what does this code do? It accepts integer n as a command line argument and writes a binary representation of n to standard output. Notation doesn't handle negative integers. So again, this is fairly technical. For example, if I want to convert the number 19 to its binary format, 10011, you can do this by hand if you are familiar with it. This is binary representation of the code. So you have to know how to convert this and the formula for that. But what is shown here, that is 2 while loops that are being used. The first one is to compute a v. It's the largest power of 2 to the power 2 less than equal to n. Work out what v is, and then cast out the power of 2 in decreasing order. And we have a while loop with an if condition to work that out. Okay, how do we convert 21 to its binary representation? Let's check that out. So Python, this is called binary 12. So this is 1100. It's binary representation. And if you do it by hand, this is what you get. Monte Carlo simulation using the Gamble-driven problem. So Gamble starts with a certain stake, has certain outcomes, and one approach is to use Monte Carlo simulation using coin flip method. What are the chances of winning? How many bets until win or lose? So this is say you can implement this using the flip methodology if you want. Various ways you can implement this. If only one statement can use the end of line style, otherwise we choose a block statement to execute this. So we use standard random.uniform. Here we're using built-in library. So let me change this to standard random and uniform. Make this blank. So this would be less than 0.5. Modifying the code a little bit. Should still work. Standard std random.uniform. Yeah. I need to import std random. There we go. So this is the Gambler's Ruin. Here's actually the code for it. And it gets accepts an integer command line argument for stake, goal, and trial count, or trial count. Run trial count experiments to start with a stake dollars and terminates on $0 or goal. Right to standard output, the percentage of wins and the average number of bets per experiment. So a bunch of inputs we're taking, and we have a for loop to work out to limit the loops for the amount of trials we want, and a while loop that checks 2 conditions: cache is 0 or cache is less than goal. If either of these fail, we're going to exit. If one of these fail, we'll exit the while loop. That's why we have and here. If it was or, one of them can be still true. Simulate the bets with the if and else condition, and then check the number of wins with another if condition as well, and you write that to output. So I can run that as well to get for example, number of wins and bets as well. So digression, simulation analysis, probability of winning a stake, 20% chance of turning $500 into 2,500. So pretty low, but expect to make $1 million one bets. Those facts can be proved mathematically for more complex scenarios. Computer simulation is often the best and only plan of attack. So estimate the output of the following gambler values 400, 600, 1,000. So this was one of them. Can do 400. And that's what you get. Estimate the output, and we can get the following. And here's a way to also work that out as well. Even stripes. Modify the divisor pattern so it produces the following pattern. Where's the divisor pattern? Here we go. So the condition just needs to be changed to if j j modulus 2, it's C plus pattern. There we go. Control flow summary. So control flow sequence of statements that are actually executed in a program. Conditional loops enables to choreograph the control flow. Straight line programs, all statements are executed in a given order. Conditionals, certain statements are executed depending on the values of certain values. If elif loops, certain statements are executed repeatedly until certain conditions are met. So these are while and for loops. So debugging. So debugging is 99% of program development in any program language, even for experts. Bug and mistake in the program. Debugging, process of eliminating or finding those bugs. You have to first find them. You'll make many mistakes as you write programs. As soon as you start a program, we found out to our surprise that it wasn't as easy to get programs right as we had thought. I can remember the exact instance when I realized that a large part of my life from then on was going to be spent in finding mistakes in my own programs. Impossible ideal. Please compile, execute, and debug my program. Why is this possible? Well, stay tuned. Bottom line, programming is primarily a process of finding and fixing mistakes. And it's important to learn from mistakes. That's how you get better at programming. Debugging is challenging because conditionals and loops dramatically increase the number of possible outcomes. Program structure, no loops. Number of execution sequences is 1. In conditionals, 2 to the power of n, 1 loop and no limit. Most programs contain numerous conditionals and loops with nesting. Good news, conditionals and loops provide structure. It helps us understand our programs. Old and low-level languages have a go-to statement that provides arbitrary structure. Elementary go-tos was controversial until Edgar Dijkstra published the famous note, go-to considered harmful in 1968. Quality programming is decreasing function of the number of go-to statements in the programs they produce. Debugging program, I'll run an example. So problem, factor a large integer in. Application cryptography. Surprising fact, the security of internet commerce depends on difficulty of factoring large numbers. Consider each integer I less than n. Well, I divides n evenly. Print I is a factor of n. Replace n with n over I. Rationale, any factor of n over I is a factor of n. I may be a factor of n over I. So let's have a quick look at the code. Import our libraries. Find a function. Get an input. Start with I equals 0. Our condition is I less than equal to n, while n is modulus I. Cast out right factor in floor division by I and send an output. So this program has bugs. The bug looks like this I plus equal to 1, I would think, and check if you have 2 while loops. This probably might go go for infinity. So is your program a real legal Python program? Python compiler can help you find out. Find the first compiler error, if any, repeat and result. So the first one is there is invalid syntax. There is a colon that is missing. So if you wrote out this code, good way to check out, find a bug, write out the code, see if it works. So the first error is there's no colon. After 0, you need that for while loops. So that's the first legal program, still has bugs. So, and the little pic here is trying to tell the computer what to do is sometimes difficult. We have to translate it into the language that they understand. So does your legal Python program do what you want to do? You need to run it to find it out. A good way to find a debug is to run the program. Find the first runtime error, if any, fix and repeat. So here it says list index out of range. You'll see this message for the number 98. So the important thing that was left out was I need to start at 2. Since 0 and 1 are not factors, your program will crash. So this is understanding more so how the math works for the code and how it was initialized incorrectly in the beginning. So focusing on testing, does your legal program always do what you want it to do? You need to test out many times of inputs to find it out. Add trace code to find the first error, fix the error and repeat. So traces are just writing out lines of code to help you figure that out. So writing on standard write line. And print out the examples, print out the variables so you can see, is it changing correctly? This is what they have done. So here they commented out, but it's useful to add this trace. So trace is like a debug line. So we know what variable and factor we are currently working on. So program development in Python is a 3-step process with feedback. Edit your program created by typing on the computer's keyboard. Result a text file such as factors of pi. Compile it to create an executable file. Use a Python compiler. And the result is a Python bytecode file. Mistake, go back to 1 to fix it and recompile. Run your program, use a Python interpreter. Result, your program's output. Mistake, go back to 1 to fix. So there's always going back to fix, back and fix, back and fix. And this is your program's loop. Where we left off with this program, this eventually gave the correct output once it was fixed with the 2 fixes, which is initializing add correctly to 2 and adding your colon. Performance. Is your working program fast enough to solve the problem? You need to test it on increasing the problem sizes to find out. You need to change the algorithm to fix it. Change the algorithm to check when I times I bigger than n, since all smaller factors are already checked. Consider each integer, I is less than n, I times I less than n, or I divides n evenly, print this out. So again, this is fairly technical math example, but hopefully you don't have to understand the math too much. Just take it maybe as coding practice, playing around with while loops and if statements and whatnot, and debugging as well. So no need to check all I equals less than n. You can just update by saying I times I is less than or equal to n. Performance analysis, how large an integer can a factor? Well, you can see digits, how long it takes, and why performance matter, because some factors will take years to work out, some hours, which you don't really want to do. Note, instant commerce is still secure. It depends on difficulty of factoring 200-digit integers. Experts are still trying to develop better algorithms for this problem. Debugging your program summary. So program development is a 4-step process with feedback. Edit your program, compile your program to create an executable file, run your program to test that it worked as you imagined, test on your program on realistic and real input data. And this process goes back always to editing your program, finding error, going back to edit, find the error, edit, find the error until it finally works. Then you submit your program for independent testing and approval. Here's some useful use sources, or the pics that we're using for the image sources. All right, and that's it for this lesson. I hope you learned something. Until next time, thank you very much.